Alright, so moment of truth. I'm about to attempt to strike my very first TIG arc. I wire wheeled off to bare metal here for my ground clamp, and I wire wheeled off a section right over here to bare metal where I'm going to try and attempt to initiate the arc. Mr. Scott Henyon, regular viewer of my channel, was kind enough to remind me, or inform me I should say, that there's one more test that I hadn't done with the welder to verify whether or not everything is working correctly. When I was doing on the last video, I did some preliminary tests, made sure the high frequency when everything was working. And the test he was mentioning is the start circuit. The high frequency on this welder, there's basically, you can shut the high frequency off completely, and then there's two other settings for the high frequency, which is high frequency start and high frequency continuous. High frequency continuous means that the high frequency is constantly on during the entire weld process, and that is used to aid in cleaning the oxide, the cleaning action for the oxide coating on aluminum. At least that's my understanding of it. So that's really the only one to use that on aluminum. The high frequency start, the way that works is when you have it in the high frequency start position, when you bring the TIG torch tip, the tungsten, within a certain distance of the metal, the high frequency arc will jump to the surface of the metal and create a low resistance circuit path for the current to flow and initiate the arc, thereby eliminating the necessity for a scratch start where you actually scratch the tungsten on the surface to initiate the arc. So I like that. That makes it easier for a noob like me. And then the way the start circuit's supposed to work is the start circuit is supposed to sense when the arc has started and shut off the high frequency. And I think I read somewhere that like in so many cycles, whereas when they're talking about cycles, they're talking about the AC waveform, how many times the AC waveform makes a cycle, that in like very few cycles, like I forgot how, it's ridiculously quick, that circuit's supposed to shut down. So when I strike hopefully we're going to initiate an arc, and once the arc is initiated, hopefully the high frequency circuit will shut off. If the high frequency continues to stay on, it means I've got a problem in the start circuit, and we'll have to investigate that. So I'm just wearing these gloves here. I just picked up some TIG gloves, but I didn't bring them. I forgot to bring them down to the shop tonight. These are stiff as hell, so these aren't very good TIG gloves. But they'll protect my hands, and I'm not planning on feeding any wire tonight, I don't think. I'm just gonna play around with if we can initiate an arc, and play around with how the pedal works. I just rehabbed my pedal. You guys probably will see a video of that where I put up a separate video just on the pedals alone, because I figure there's a lot of people that might have those pedals and might want to have some tips on how to clean and rehab those and test them and make sure they're working okay. All right, so let's get going here. So I got to set up. I got to get my cooler running, because I don't want to forget to turn the cooler on, obviously, or otherwise I'm gonna ruin my brand new cable for the TIG torch. And I got to get my helmet. All right, just thinking and making sure I got everything I need. So hopefully this won't make too much smoke. If it makes a lot of smoke, then I'm probably going to have to hold off because it's later in the evening, and if the smoke alarm down here goes off, it's tied into all the smoke alarms in the house, and I'm going to have a major problem in my hands because it's going to wake up all the kids who have school tomorrow. So, all right. Definitely not getting a good, I'm not getting a good ground here. I think I did some bad things to that tungsten already. Well, I think I'm actually touching the metal to initiate the arc, so I can hear the high frequency working, but it's not really doing anything. But there's a high frequency intensity control that I haven't touched, so I'm thinking I might try and turn that up. And then when I did initiate an arc, it didn't look like it was doing much to me, so I floored the pedal, and when I floored the pedal, it didn't take long to burn a hole right through this metal. So obviously I've got a lot to learn. The good news is I'm able to actually get an arc. So let me try and readjust that high frequency a little higher and see if that doesn't solve my problem as far as starting. Because my understanding was that this should literally, that I literally should see like a little bolt of lightning, almost like a big spark, like from a spark plug coil, jump and initiate the arc, and that's not happening. The tungsten now, I don't know, I should have showed what it looked like before I started, because to use tungsten in there now, so it probably wasn't that great to start. But now I think it's even, I think it's got even bigger issues. Alright, well, let me try and readjust that high frequency start and see what happens. So that knob for high frequency has numbers on it from 0 to 100. It was on 30. I just bumped it up to 50. Okay, so I got two things going on here. Let me shut the cooler off. Shut the cooler off so you can hear what I'm saying better. But two things going on here. First thing is, I'm still not getting any high frequency start, although clearly from the activity over there at the spark gap, there's plenty of high frequency being generated over there. So I'm not quite sure why this isn't working. I tried that control, I turned it all the way up to 100, still no high frequency. Then when I finally did touch off and get it to start, and I eased off on the pedal so I could see the plasma ball more clearly. I was looking at it. It was looking kind of weird to me. And then it suddenly struck me. I never turned on my argon supply. So I've been I have been doing all this with no shielding gas. Alright, let's try this again with some argon. So I think I'm going to call it quits for tonight because it's kind of late. I'm going to have to do a little bit more reading up and see if I can't figure out why I'm not getting high frequency start. And also, I think I need maybe some clean metal. This metal, I just wire wheeled off a small section of the paint off of this metal over here. But I mean, attempting to weld with the gas off, I think made kind of a mess over here. Does seem like I was able to actually do something over here though. It's working. It's just, I think I need to work out some kinks, and then I also just need to learn what the heck I'm supposed to be doing. So you can see the hole there on the left that I blew through. And then over there, that area right there was where I was just attempting to weld a little bit with the gas on. Well, it's been a couple of days since I was down here striking arcs. My first TIG torch arcs with this thing. And what I discovered was that I'm not getting any high frequency start. And I'm not quite sure why yet, so that's what the next little thing we're going to do. But I figured I'd take a moment to explain the high frequency start circuit on this welder for those of you who aren't familiar with these ancient Airco and Miller setups. And oh, by the way, this design was continued, the use of this was continued in the Heliarc series of welders with high frequency, and I think even the Synchro Waves used a version of this. You know, slight differences here and there, modifications as they went. But essentially what this is this is a there are different ways you'll hear this referred to, but the circuit in question is most commonly known as a spark gap oscillator. What it technically is it's an LC circuit, and the way it works is really incredibly simple. And it's not uncommon for this to be used in some Tesla coil designs, and there are some people who still experiment with spark gap transmitters and receivers, because the whole idea was back in the very early days of radio, long before they were transmitting voice. They were transmitting code, and before they were able to transmit tones, they were transmitting basically sparks. Anyways, not going to get... here we go again, getting off the track again. All right. So here's basically what we have for a circuit. We have behind here, amongst all those transformers that are in this beast, there is one transformer in here that's generating high voltage for the high frequency start circuit, or I should say the high frequency circuit, because depending on which position the switch is in, it's going to either run continuously, not at all, or for start. The way it works for start is there's a relay inside there, and I believe there's a resistor in there that is set up so that once the voltage drop across that resistor gets to a certain point, it will cause the relay to de-energize. The contacts on the relay will open and shut off the transformer that's fueling this high frequency circuit. When you put it in continuous, you're bypassing the contacts of that relay, so that transformer, the high voltage transformer, is just always getting juice when the contactor is closed. Okay? If that makes sense, hopefully. So when the transformer is getting power, it develops a high voltage, and the high voltage is sent
through these two capacitors. Now these two capacitors are in parallel, but the high voltage is sent through them in series. Okay, so I'm going to draw a diagram, a quick diagram of the circuit. But all you need to know is that basically the high voltage coming out of that transformer is going in through one of these copper bands, through the two capacitors in parallel and out. The reason why there's two capacitors here in parallel is because the voltage rating that's required. The capacitors are actually 0.002 microfarad capacitors. I said that weird. 0.002 microfarad capacitors. When you take capacitors and you place them in parallel, the capacitance adds. So this circuit with these two strapped together in parallel like this is actually 0.004 microfarad capacitance is what the circuit sees. It's the exact opposite of resistors. With resistors, when you put them in series, they add, and when you put them in parallel, there's a formula. So anyways, these are in parallel, so the effective capacitance of this looks like one big 0.004 microfarad capacitor rated at like 6,000 volts. In later models, they beefed this up, I believe. As a matter of fact, in some schematics, this appears as one capacitor, and in the parts list, it's listed as one capacitor. I haven't seen yet what the value is that they put in there. I'm kind of interested about that. What this block right here is, okay, this block is what's called a spark gap. There's actually two spark gaps in here. So what this is the power is coming in through here, goes across this spark gap when the spark actually crosses the gap, and this is common with this, so then it flows through, goes across this gap, and comes out here. So effectively what we've got right here are two spark gaps in series. These two spark gaps that are in series are actually across the output of the transformer. So what happens is, when the output of the transformer reaches its maximum, because we're talking about AC, so we've got an AC voltage that's jumping up and down. When it reaches maximum output and it's charging these caps, when it reaches maximum output, the little tiny airspace that's in these spark gaps which is acting as an insulator to a point, can no longer withstand the potential that's present. And what happens is the spark jumps these two gaps, okay, and effectively this suddenly appears to have a very, very low resistance. It actually looks like a short right across the output of that transformer for a fraction of a second. And discharges this capacitor through another transformer, which we can't see. It's behind here. And it's funny, they call it a transformer, but the thing almost looks like a big coil. It's a big, huge inductor, but it's got another wire wrapped around it. And one of the wires is actually in the circuit for the current coming out to the output right here, to the electrode. So effectively, it's acting like a transformer that allows that high frequency to be imposed, or superimposed, I should say, onto the output here, so it can ride along that lead out to the torch. So let's look at this on paper. All right, so let's look at a schematic of this circuit. This is pretty good representation of the circuit. Actually, it's almost identical to what's in the schematic diagram for my particular welder. What we've got here is we've got a primary for the high voltage transformer. Okay, on this primary is 120 volts when the contactor is closed and the start switch is in continuous
I'm sorry, the high frequency switch is in continuous. There's 120 volts on this primary whenever the contactor is closed. When it's on start only, what happens is there's a relay contact in this primary circuit, and there's another circuit that's involved with making sure that once the arc is established, that relay opens and de-energizes this primary. But from here over, this is the high frequency circuit. So we've got a high voltage secondary. So this transformer is a step-up transformer. It's creating several thousand volts. And what we've got is a very simple LC, or inductance capacitance, oscillation circuit to generate high frequency. The way it works, here are our two capacitors, and they're in parallel. So the circuit really sees these two capacitors as one capacitance, and we talked about just a minute ago why they're using two, basically to get that voltage rating. So and over here we have another inductor, which is actually part of almost like a coupling transformer. And on that secondary of that transformer, as you might want to call it, we've got the actual line that's supplying the output current to the, this is the connection on the welder for the electrode. So the high current coming out of the welder comes through here, goes through this coupling transformer and out to the work. So what happens is the high frequency that's generated by this circuit gets superimposed over the current that's flowing to the welding electrode. Alright, so I'm going to clean this schematic up, and it'll be much clearer what's going on. So if I omit this secondary over here that goes to the electrode, and I turn this capacitor into one capacitor, and I just move it around the corner here to clean it up a little bit, I end up with this circuit. And this is a basic spark gap oscillator. So again, we've got the 120 coming in the primary, we've got a high voltage secondary here, and then we've got essentially a capacitor and an inductor, an L inductor and C capacitance in series. These are your spark gaps. The spark gaps are in series. So in effect, we've got a spark gap, and then it's followed by another spark gap. These spark gaps are set very precisely at 0.008 thousandths per the spec of the welder. I have seen on numerous websites people saying that they've been told that they should increase the spark gap to 10 or 12 thousandths, and that helps with their high frequency start problems. And it certainly would help, and I'll explain in a moment why that would help and what the problem with that potentially could be. All right, so first let's talk briefly about how this circuit's going to work. What ends up happening is these gaps right here have air in them, and the air is an insulator. And it's a pretty good insulator to a point. So what happens when you first energize this circuit is there's a high voltage on the secondary, comes up, and at first the high voltage can't bridge these spark gaps. So what happens is it charges this capacitor, and as this capacitor charges, the voltage, output voltage, rises. When the output voltage gets to a certain point where it can overcome the resistive path of the air in these two spark gaps, an arc or a spark occurs across the two gaps, because suddenly that voltage now takes this path. So what happens is, when you first power up the circuit and the voltage starts rising, this is all happening in milliseconds. When you first power this up and the voltage starts rising, all the circuit really sees is this. Okay? When the voltage reaches that critical point where it can jump those spark gaps, what happens is the spark gap circuit right here, this part right here, suddenly becomes a very low resistance path, and all of a sudden we're left with a short circuit across the secondary here. What that short circuit across the secondary does is it creates a situation where this whole part of the circuit now, if I just drew a line right there, well, what you can see is I've got just a series circuit. And what happens is this capacitor, which, if everything's timed correctly, has pretty much reached its full charge, suddenly discharges through this inductor. And it gives it a good sized kick. As soon as this capacitor discharges into the inductor circuit here, well, what happens is then this voltage drops and can no longer, and the arc or the spark that's causing this short circuit to discharge this whole thing can no longer be sustained, and then this goes back to an air gap. Once this goes back to an air gap, the short circuit is effectively removed across the secondary, and the secondary is allowed to start charging this capacitor again. And the process starts all over again. And the rate at which this discharge, recharge, discharge, recharge happens is going to be the same rate at which these sparks are going to be occurring, which is going to be the frequency of the output. It's going to be the output frequency of this circuit. Hopefully that makes sense. So this is a pretty common circuit used in a lot of Tesla coil designs, and all that they do in a Tesla coil is they typically make this inductor right here the primary winding of the high voltage transformer, or the Tesla coil itself. So what ends up happening is your secondary winding of the Tesla coil is going to be many more turns than this primary, and you'll end up with that really high voltage at the output there, which so many Tesla coil aficionados love. Matter of fact, I actually, those of you who follow my videos regularly, you saw that I was playing around with an old microwave transformer. We scrapped the microwave and had a transformer. We were just kind of making sparks with it and goofing off and everything. This actually would have been a good circuit to build with that transformer. This transformer right here would be the microwave transformer, and then we could easily have built a spark gap. Matter of fact, I even have an extra spark gap from a welder that I scrapped. You know, maybe at some point I'll sit down and I'll make something, a circuit like this, and we'll see if we can't play around with it. I want to get back to the spark gaps. So the spark gaps, as I mentioned, they're set at 0.008 thousandths. And people said, well, they increased the spark gap, and by increasing the spark gap, they were able to improve their high frequency start. That would be true, because effectively, if we increase the spark gap, if we make this gap larger, we're making the airspace in here that much larger. So it's that much more difficult for that voltage to jump that gap. So what happens is, if the gap's too large, well, then this secondary voltage will reach its maximum and not be able to jump across the gap, and so then this capacitor just fully charged and charges, and the circuit just sits here and does nothing. So it basically isn't an oscillator and doesn't do us any good. But if we open up this gap a little more, but still leave it close enough so that at some point when the voltage reaches its highest point, it can jump the gap and we can still get oscillation going. And obviously what we're going to end up with is this capacitor is going to charge to a higher voltage before that breakdown occurs that causes the circuit to discharge. So we can continue to increase this spark gap until we reach maximum voltage that the circuit's capable of. So if we increase it too high, again, we won't get oscillation. But the problem is, if we increase it and we can still sustain oscillation, we've got to keep in mind that we're now increasing that voltage, which is why the high frequency works better, more robust. Only the problem is you're putting more of a strain on this capacitor mainly. This is the weak part of the circuit. So I think the original capacitors that are in there are rated for 3 or 4 kV or 3 or 4,000 volts. I think later ones they went to 6,000 volts. And then I think I even read on some of the forums that some of the later synchro waves in that even went to like 10 kV or higher capacitors. So if we can do like Mr. Scott Henyon had mentioned, I think on one of his pages, what he did was he found some higher voltage capacitors, put them in a series parallel circuit. He mentioned series parallel, so I'm guessing Scott's probably watching this video. I'm guessing what he did was he made a circuit like this. So I've got 4 capacitors here. I put 2 of them in series and 2 of them in series, and then I take those 2 series circuits and put them in parallel with each other, and I end up with one capacitance that he then stuffed inside of the original can for the oil-filled mica capacitors there, and put some potting material in there. And I don't mean like soil, I mean epoxy. And basically built a supercapacitor to replace these here. These are still available. These caps are still available from, I believe, Miller for Less, if I'm not mistaken, but they're over $100 a piece. There are numerous listings on eBay for high power capacitors that don't fit that. There's actually some listings on there right now. I noticed there's somebody on there that's selling used, what they're calling RF caps, high voltage. And what they're doing is they're stripping these out of high power transmitters by the looks of it. And the question is, you know, how good are they? They are used caps, so you gotta roll the dice there. But anyway, so that's the circuit. Oh, I almost forgot. So my point is that if you did something like this here and you put some wunderbar capacitors in here that could really take the voltage, then yeah, sure, increase the spark gap and go to town. Oh, I forgot one thing. This high frequency control, this is a rheostat, variable resistor, okay? This rheostat is in series with the capacitor. You can actually see that strap coming from the capacitor goes right to this wire, and this wire here goes to that coupling transformer that's behind here that you can't really see. So that's how they're varying the intensity of the high frequency, by putting this resistor in series. Okay, so I should have drawn this on the schematic, but I wanted to keep it a nice clean LC oscillator spark gap circuit. Okay, so my apologies. These are the 2 capacitors, as I had already mentioned. The other thing I forgot to mention about these is if you get one of these welders and you see black goop oozing on this nice pink fiberglass behind here, chances are it's leaking out of these, and either one or both of these are bad. And chances are if one's bad and they're identical, they're the same age, you're probably going to want to change them both out. This capacitor right here,
This device here is a resistor. It's called a bleeder. It's actually it's doing a couple different jobs, but this capacitor right here, I actually have no idea what this capacitor does. So my apologies. One lead of this capacitor is going over to this big wire wound resistor, and the other lead goes through a hole back here and disappears somewhere into the welder. I don't know where. I don't even think this is in this circuit, the high frequency circuit. I think it's just happens to be located out here. I might be wrong on that, so I'm not gonna really talk about that, but I just wanted to mention in case you guys are wondering. But it's definitely not in the secondary part of this circuit like the circuit I drew. All right, now let's get into some nitty-gritty diagnosis here. Why isn't my high frequency working? All right, well, possibility number one. Possibility number one is that my high frequency is working, and it's working perfectly normal, but that it's just not getting to the end of the TIG torch. And there's a couple of ways that that can happen. A lot of people have worked on these and said that they found that coupling transformer behind here, that when they opened up the unit and looked at it, that it was very dirty, had a lot of dust, debris, and everything stuck in it. Some had even said they found metal shavings in there, so that, you know, it must have been in a machine shop situation, and you know, they had machines nearby that were throwing shavings into the welder, which you can imagine is probably not the greatest thing to have. And that all they had to do was clean up that transformer, that coupling transformer, and the coupling transformer looks like a huge coil, really. But we'll take a look at that, or I'll show you one because I've got a spare one. So you could have a situation where the high frequency is being bled off, is the term that's often used, meaning that high frequency is migrating to ground somewhere before it gets to the tungsten on the TIG torch. So that's one possibility there. So we could have a circuit that's working correctly, but something else is going on. I even saw one reference that somebody made and said that, well, you could have bad coolant if you're using a water-cooled torch. You could have bad coolant that could cause a problem. Well, it's like, how the heck could that possibly affect anything? Well, I'll tell you how. If your coolant is, if something's happened with your coolant where it's become highly conductive, you might have a problem with it bleeding off, because, as we know, this is the power block right here. Okay, this is the cable or the wire that's supplying power to the TIG torch head, but it's filled with the coolant. The coolant's being pumped through here. Okay, so we know the coolant is in direct contact with the output here. Okay, the coolant also is flowing from and back to our cooler. In fact, this is the output from the cooler going to the torch head. Okay, so we know that there is a potential current path from the torch head back here to this pump. In this particular case, on my pump, the pump appears to be of solid brass design. So we've got a nice conductor there. Okay. So the question is this at ground potential? Well, let's do a little test, shall we? Okay, so I've got my cord here for my cooler, and we've got a ground pin here. So this is how this unit is grounded for safety. All right, so if I connect one side of my ohm meter to my ground pin, and then I take the other probe and I touch this brass fitting right here, I can see that I have zero or virtually no resistance, meaning, you know, the body of this pump and all the fittings and everything are grounded. So all that high frequency has to do is migrate along the coolant lines, the coolant inside the lines, and it's going to be pulled down or bled off by the cooler to ground
through the cooler when it's plugged in and running, which is, of course, anytime you're welding. So the question is, well, how bad is that affecting us? Well, obviously, it can't be a dead short, because then we would have our output current at the torch wanting to go back through the coolant, through the cooler, and through that ground, instead of actually going through the work into the grounding clamp. Remember, electricity wants to follow the path of least resistance. But high frequency acts a little bit funny, so I'm going to keep that in mind. So remember, I just said high frequency acts kind of funny. Well, case in point. Another thing that was brought up on some of the forums is, hey, make sure you don't have any loops in your lead, in your torch cable. All right, I just happened to notice the other night when I was trying the torch out for the first time, I hadn't noticed that this is what my cable was doing. I've got 25 feet of cable here, and because I'm so close to the welder, I just left it on the ground, and it just so happens, look what it's doing. It is all looped up. And apparently, because of the way high frequency acts weird, that right there could be killing my high frequency.